Hello everyone. In this Expo presentation, my colleague Tori and I are excited to present on the topic of applying AI to enable the autonomy in robotics using MATLAB. As we all know, robotics is an exciting and rapidly advancing field, and autonomy is becoming increasingly important in many applications. By leveraging AI techniques, such as deep learning, you can enable robots to make a more intelligent decision and operate autonomously in a wide range of environments. With MATLAB, we have a powerful platform for developing and testing these AI algorithms. As you can see from the video, DLR's Justin robot is able to use tactile information and deep learning to perform dexterous manipulation of a cube. Additionally, with the help of the deep learning and optimization-based motion planning, Justin robot can navigate complex environments quickly and efficiently. So in this presentation, we will be discussing the potential of AI in robotics and showcasing some real-world examples of how MATLAB is being used to develop and test these algorithms. As we continue to explore the potential of AI in robotics, it is important to understand the need of our customers and how they currently use AI in their robot. To that end, we conducted a user study using over 60 data sources to understand how our customers currently use AI in robotics. First, where is AI being used in robotics? Let's take a closer look. AI is used in robotics for perception, planning, and control. We also found that some robotics engineers are doing others like wireless system to bring AI for cobot and designing smart batteries. Not surprisingly, we found that our customer primarily use AI for the perception compared to the other workflow steps. Why is that? The reason why they use AI primarily for perception is because it is a critical step in enabling other part of the workflow. Safety, robustness, and certifications matter for production. And traditional algorithm has an advantage of AI in this regard for the planning and control. But recent advancement in AIs are enabling new approaches to planning and control. In the next few slides, we will explore some of these AI-powered perception, planning, and control applications in robotics. We also uncovered several pains and challenges that robotics engineers are facing when implementing AI-powered solution. Why does these AI projects sometimes fail? There are people's problems, such as lack of AI expertise. Data problems, including insufficient data, can hinder the development and performance of AI model. Tool problems arise when engineers need to integrate AI models into the broad system and deploy them effectively. Finally, business problems such as poor ROI can also be a challenge. So with that, I would like to hand over to my colleague Toru, who will explore how MATLAB can help address these challenges and enable the development of robust AI-enabled robotic systems.
Thank you, YJ. I'll be addressing the AI-driven design workflow, wherein deep learning and reinforcement learning are effectively employed. The core elements of robotic systems design are perception, planning, and control. Around this core element, you have a robotics platform. You need to deploy your implementation to the robot. System modeling and simulation will ensure your robot to meet customer needs. We are going to use the diagram as a guideline to explain how MATLAB can help you with AI for each element. Now, for the perception part, I will use an intelligent bin picking application for a collaborative robot arm or cobot. This shows how the cobot perceives the environment to perform a pick and place task. Here is the example of pick and place task with a cobot to show how AI can be integrated into the system. The RGB camera mounted on the robot arm captures RGB and depth images to detect PVC pipes and estimate their poses. With similar shape and color, PVC pipes are difficult to classify using a traditional rule-based algorithms. However, by utilizing the AI model, we can easily classify the type of PVC pipes. To train an AI model to detect bug pieces, a huge number of training data are required. Acquiring many data from real hardware is difficult and limited. However, by using a simulation, a large number of the data can be collected in a short time automatically. In addition, the shape of the bug pieces, writing conditions, background, and so on can be easily changed. This makes it possible to generate the image of various scenes that are difficult to produce in real world scenarios. On the other hand, it is necessary to collect the training data from the real hardware to improve the accuracy of the AI model. The acquisition step can be also automated using out-of-box path planners. MATLAB Simulink have various examples of the generating the synthetic dataset through simulation. For example, semantic segmentation for UAVs using the Unreal Engine, LiDAR sensor models to generate the point cloud, and camera images using a gazebo simulation shown here. This is also very helpful to take into account rare events. Data labeling is a crucial aspect of AI design workflow, but it can be also time consuming. Now, I'd like to show an automated labeling tool we have. When we utilize the synthetic data, those synthetic data already contain the ground truth of the bounding boxes. Then we can train an object detector using only the synthetic data. But the accuracy of the detector train may not be sufficient, so training with the real-world images is still required. Image label app can be used for interactive labeling of actual acquired images from camera. In addition, by utilizing the automation function, the labeling effort can be drastically reduced, as shown in the video. Next, you will manually fix only those areas where the detection results are inaccurate. The rest of the process is retraining with the labeled actual images to improve the accuracy of the object detector iteratively. Of course, it is important to have direct access to many AI algorithms and pre-built models. Examples are the way engineers to learn how to use AI models and find the best approach for their specific problem. For example, object detection with EuroB4, instant segmentation with Muscle CNN, and semantic segmentation with UNet. We provide hundreds of examples for building AI model in a wide range of domains. We also know that the broader deep learning community is incredibly active and the new models are coming out all the time. Because we support the important models from TensorFlow, Pilot, and Onyx, you have access to those new models and can work with them within the MATLAB environment. Next, let me talk about the AI application in path planning. I will showcase how AI can be utilized by the UAV for path planning within an environment. As YJ explained in the previous section, AI is currently primarily applied in the perception field in robotics applications. For example, let's consider using the UAV to create a road map of our city. First, we obtain image data using a camera mounted on the UAV. Next, we classify roads and buildings using a semantic segmentation AI model. Then we stitch each of the classified patches to reconstruct a single occupancy map. Next, how can we efficiently plan the flight path of the UAV? Traditional rule-based explanation algorithms have been widely used for path planning. However, one of the challenges of those explanation algorithms is their execution time. To address this challenge, we have a deep learning-based sampler that improves the execution time. This approach implements a conditional variational autoencoder that generates a round samples for a given map, start state, and goal state. By leveraging the latest version of MATLAB, you can apply AI models not only in perception fields, but also in other areas, such as planning. This brings us to the rest of the workflow of autonomous algorithms, which is making decision and control. For this, I will showcase an example of the obstacle avoidance for a delivery mobile robot in a dynamic environment. The obstacle avoidance algorithm executes a series of maneuvers while simultaneously sensing and avoiding obstacles in tight spaces. This complex task requires fine-tuning of the hyperparameters, which can be time-consuming. To address this issue, we leverage reinforcement learning. We first train an agent on a simple scenario map, which facilitates the convergence of reinforcement learning. After the training within the simple map, the agent gained the fundamental obstacle avoidance ability. Then the agent can be trained efficiently within a higher fidelity Unreal Engine environment and performing fine-tuning. Reinforcement learning toolbox simplifies the complex workflow, and the simulation environment can be easily scaled up. Now, I will discuss how AI can be used in the part of the entire robot application. Looking at the overall system, AI is often part of a larger system. You can have each functional component of perception, planning, and control as autonomous algorithms. And you can also integrate them into a robot platform, which includes robot dynamics and sensor models. Sensing and the robot API can be either real hardware or simulation models. With a model-based design approach, the model can continue to evolve, and you can scale this model for different applications as necessary. As a closed-loop system, system simulation is crucial in verifying that AI models performed as expected in various environments. With MATLAB, you can dynamically spawn the robot arm and the work pieces at runtime. The objects spawned in the virtual environment can be easily modified. We can easily reuse the simulation model for another robot, such as Universal Robot, due to the modularization of each block. The end goal of the task is to pick up the cuboid-shaped objects distributed in the view. The hardware interface can be easily switched to Universal Robot's cobot, leveraging a dedicated hardware support package for Universal Robots. Each robot application may have different deployment requirements, whether it is on an edge system for production lines or a cloud-based streaming system receiving data from a number of robots. So your AI models need to be able to deploy to any possible platform. We have a unique code generation framework that allows models developed in MATLAB Simulink to be deployed anywhere, such as CPUs, DPUs, microcontrollers, and FPGAs, without having to rewrite the original model. Automatic code generation eliminates coding errors and is an enormous value driver for any organization adopting it. Let me show a deployment example of the pick-and-place robot application. It is necessary to implement the AI models on edge devices to make the robot operate autonomously and in real time. In this example, the Simulink model of the pick-and-place algorithm is generated as a CUDA ROS node by using a ROS toolbox and GPU coroller. The generated CUDA ROS node is built and executed on top of ROS system and NVIDIA Jetson, and object detection can be performed at a high speed by leveraging the embedded GPUs even on edge devices. With that, I'd like to hand over to the presentation to YJ to summarize our discussion. Thank you.
Thank you, Toru. Before I wrap up today's talk, I would like to share our customer story. Astri in Hong Kong used MATLAB and Simulink to create a model-based digital twin with computer vision and deep learning algorithms for their welding robot, which reduced integration time by 40% and development time by 30%. This approach helped Astri move to smart manufacturing to meet the customer demand and address rising costs, and inspire confidence in a model-based design approach. Combining MATLAB and Simulink brought the digital and physical world closer together and offer a level of automation and real-world simulation that accelerate engineering process. Today, we discussed how to empower your robot using AI for perception, planning, and control in autonomous robotics application. MATLAB and Simulink with AI provide an integrated design environment for your autonomous system from design, simulation, and deployment in the same platform. In summary, with MATLAB and AI, you can build a dataset by capturing and labeling images obtained from simulated and real-world scenarios. You can use image recognition and object detection techniques to build the map, estimate the pose of the object, and detect the dynamic obstacle. You can speed up the path planning by training a deep learning-based sampler and use reinforcement learning for the robot control. Finally, you can integrate AI model within model-based design workflow and build a system-wide simulation and test with AI model. Do you remember these challenges that I discussed earlier? So let's see how MATLAB makes these challenges a bit easy. First, data complexity. MATLAB is a great modeling and simulation tool and provides automated labeler for different modalities of the data. Secondly, model complexity. With MATLAB Simulink, we have an easy access to pre-trained model with a single line of code. You can use a model developed in MATLAB or those available in open source framework like TensorFlow and PyTorch. By building a system-wide simulation with AI model, you can validate the behavior of a digital twin before physical execution with robot hardware. The majority of the successful AI project in robotics has been made possible by a clever combination of an AI model and robotics algorithm acting together. So robotics engineers need to leverage their domain expertise and apply AI solution for successful projects. So I think you can be an AI expert with MATLAB. Finally, by leveraging the powerful capability of the MATLAB Simulink, you can really achieve successful AI-enabled robotic project. If you'd like to learn more, The next best step is to get started with deep learning yourself. To do this, simply open your browser and launch one of our free online tutorials starting with deep learning on LAMP. In addition, we have a large number of example tech talk series and related webinar that are published on our website to help accelerate your development effort. And we will be happy to support your specific user cases as well, so feel free to reach out to us with your any question.